On the evening of June 9, 1972, a series of slow-moving thunderstorms stalled over the eastern slopes of the Black Hills in western South Dakota. Warm, moisture-rich air originating from the Gulf of Mexico was lifted repeatedly by the terrain, producing continuous rainfall over the same drainage basins for several hours. Rapid City lay downstream of multiple narrow creeks that normally carried shallow, manageable flows. Urban development had expanded directly along these channels during the mid-20th century, with residential and commercial structures built inside natural floodplains. Flood planning assumptions were based on gradual water rise and visible upstream warning signs. Rainfall intensity exceeded those assumptions within minutes. The hydrologic response unfolded faster than existing warning systems could detect or communicate. The Black Hills form an isolated uplift rising sharply from the surrounding plains, with steep eastern slopes draining toward Rapid City. Numerous small watersheds funnel runoff into Rapid Creek, a channel that passes directly through the urban core. Average June precipitation in the region is moderate, and historical flooding events had been limited in scale and duration. Urban expansion during the 1950s and 1960s placed housing developments, mobile home parks, and commercial corridors directly adjacent to creek banks. Channel modifications emphasized erosion control and landscaping rather than high-volume flood conveyance. Bridges and culverts were sized for routine flows, not extreme discharge. Floodplain mapping was incomplete, and zoning restrictions were minimal. Emergency planning assumed that significant flooding would provide hours of advance notice as upstream water levels rose gradually. No structural flood defenses existed along most urban sections of Rapid Creek. On June 9th, atmospheric conditions aligned to produce extreme rainfall efficiency. A stationary frontal boundary extended across western South Dakota, while persistent southeasterly flow transported deep moisture into the region. Weak winds aloft prevented storm movement, allowing thunderstorms to regenerate repeatedly over the same locations. This training effect concentrated rainfall over confined drainage basins. Orographic lift along the Black Hills enhanced vertical motion, intensifying precipitation rates. Radar coverage was limited, and rainfall estimates relied on sparse surface observations. Between early evening and midnight, rainfall totals exceeded 10 inches in portions of the watershed, with localized measurements surpassing 12 inches. Soils reached saturation early in the event, eliminating infiltration. Nearly all subsequent rainfall converted directly into surface runoff, accelerating watershed response. Rapid Creek and its tributaries began rising sharply after 9 p.m., with water levels increasing several feet in less than an hour. Channel capacity was exceeded nearly simultaneously across multiple upstream reaches. Steep gradients in the foothills accelerated runoff velocity, producing fast-moving flows carrying trees, vehicles, and structural debris. Debris accumulation at bridges and culverts temporarily restricted flow, forming short-lived impoundments that failed abruptly. Each failure released a surge wave downstream, compounding flood intensity. As flows converged toward the urban corridor, discharge increased beyond historical precedent. By the time floodwaters reached residential neighborhoods, depths and velocities exceeded the structural resistance of wood-frame buildings. Darkness and heavy rainfall eliminated visual warning cues, leaving residents unaware of the approaching surge. Initial urban inundation occurred shortly before 11 p.m. along low-lying neighborhoods adjacent to Rapid Creek. Water entered streets and structures within minutes, providing little opportunity for evacuation. Mobile home parks situated directly along the channel experienced rapid destruction as units were lifted, displaced, and fragmented by moving water. Electrical infrastructure failed early as substations and transformers were submerged, resulting in widespread power loss. Street lighting went dark across large sections of the city, further reducing situational awareness. Telephone service degraded as poles collapsed and lines shorted. Emergency dispatch centers experienced sharp increases in call volume, but lacked real-time information about flood extent due to communication outages and limited field visibility. Bridges crossing Rapid Creek failed structurally or became impassable as debris loads increased and foundations were undermined. Roadways were eroded or submerged, severing access routes used by emergency responders. Law enforcement and fire units attempting rescues encountered flooded streets and collapsed crossings, forcing abandonment of vehicles and limiting reach. Ambulance access was confined to isolated high-ground corridors. Hospitals activated emergency protocols while operating on backup power. The absence of centralized flood warning dissemination delayed coordinated evacuation orders. Many residents did not recognize the severity of the situation until water entered buildings. Flood levels continued rising until after midnight, with peak flows occurring between approximately 12:30 and 1:30 a.m. As floodwaters moved through commercial and industrial districts, fuel tanks, vehicles, and building materials became mobile debris, increasing destructive force. Impacts against structures caused progressive collapse as load-bearing elements failed. Flow velocities exceeded the stability limits of residential construction, scouring buildings to their foundations. Downstream areas experienced delayed surges as upstream debris accumulations released. Rescue operations transitioned from evacuation to recovery as conditions stabilized and waters receded. Rainfall diminished after midnight, but runoff persisted for several hours due to watershed saturation. By early morning, floodwaters withdrew rapidly, leaving behind thick sediment deposits, displaced infrastructure, and extensive debris fields across the city. Emergency response continued throughout June 10th as search and recovery operations expanded along the flood corridor. Temporary shelters were established to accommodate displaced residents. Utility crews assessed widespread damage to electrical, water, and sewage systems. Potable water supplies were compromised by contamination from ruptured lines and flood debris. Transportation networks remained fragmented, isolating neighborhoods and delaying aid delivery. Damage assessments revealed entire residential zones rendered uninhabitable. The rapid onset, nighttime timing, and concentration of development within floodplains significantly reduced survival opportunities. Casualty counts increased over subsequent days as recovery progressed and additional victims were located. The flood affected approximately 50,000 residents in Rapid City and surrounding areas. Official records documented 238 fatalities and hundreds of injuries. Property damage exceeded $160 million in 1972 dollars. Fatalities were heavily concentrated in mobile home parks and low-lying neighborhoods adjacent to Rapid Creek. Post-event investigations identified inadequate land use controls, limited hydrologic modeling, and absence of effective warning systems as primary contributors to loss of life. Long-term recovery included the removal of residential development from floodplains and the creation of greenway buffer zones along Rapid Creek. The 1972 Black Hills flood remains one of the deadliest flash flood disasters in United States history and a benchmark case in urban flood risk management.